This computer boy is always confused. I guess while people grab their food, I will quickly introduce Cindy here. So before I introduce her, the last kind of an introduction to why we're hosting this is we applied for this micro grant from Research America a couple months ago, and we're fortunate to have gotten the grant, and we've had a 3-part series on kind of making infographics and the importance of visually communicating science. And so we've had 2 workshops previously, where the first workshop was focused on learning how to create effective visualizations for other scientists. So kind of working on figure making, learning how to use Illustrator. And the second part was kind of learning how to use the tool of Canva on how to make infographics for non-scientists. And as the third and final wrap up of our series, we'll learn a little bit more from Dr. Xiong, who is an assistant professor at the University of Massachusetts Amherst right now, and who she received her PhD in cognitive psychology from Northwestern and worked on her undergraduate degrees in applied math and psychology at UCLA. So we're really excited to hear more about from her expertise and a little bit about perhaps her research on combining visual perception and cognition and data visualization. We can't wait to hear what you have to share with us.
Thank you, Kayla, for Thank you, Kayla, for the introduction. I'm going to go ahead and just share my screen, and feel free to interrupt anytime if you have questions, but I'm not cool enough to share the screen, so maybe you can make me cooler.
Yeah. My apologies. Always happens. It should work now.
Awesome. All right, so here's the screen I will share, and I will click this. I'm gonna try to monitor chat, but if I miss anything, feel free to like unmute and just catch my attention. So again, thank you for the introduction. I wanted to quickly introduce my kind of research portfolio here. I interface between data visualization and human cognition and perception. And today I'll get to talk to you more about how research and applications have been done in this space. And also just a fun fact that my last name, Xiong, it means bear in Chinese, and it's pronounced Xiong, or if you're feeling French, like the TIO and Xiong in words like visualization. And so I thought, well, I could just name my lab the Visualization Lab, since it fits the theme. But while we're at it, I might as also claim the Cognition Lab and the Perception Lab and the Human Decision Making Lab. Trademark pending, but I could go on for a while. Anyway, so that's about my lab, and the key message that I wanted you all to take home today is that you have a lot of power when you communicate data to other people. Design choices that you make in visualizations can lead to powerful and intuitive insights, or when done poorly, it can leave important patterns obscured and misunderstood. So here's an example for you. Here we have a chart depicting the number of COVID-19 cases reported over 2 weeks in 5 counties in Georgia. If we were to take a moment to look at this, the first thing you might notice is that there's this really significant downward trend. The cases are clearly getting better. You can take a closer look and realize that's actually not the case. The x-axis here, it's not sorted by time, it's actually sorted by size. So this downward trend is misleading. What's the intent? This visualization is created by the Georgia Department of Public Health, and their intention was to help people see on which day there were the most versus the least number of cases. So they sorted the bars by size to help people know that, but it wasn't very effective because this downward trend is so intuitive to notice. So you could alternatively design this visualization in the same data, but now sorts the data by county and rearrange the x-axis so it's ordered by time. Now, the pattern that stands out to you is probably how the number of cases are changing over time for these 5 counties. And it's clear that there's a bimodal distribution of cases over time. But if I were to ask you to look at this right visualization here and tell me on which day there were the least versus most number of cases, that's very difficult to do because that requires you to select the bars that are the highest and add them all up and figure out what day that was. And it's tricky, right? It's much easier to do that on the left. So what we're seeing here is that there are these two designs made you see very different patterns in the same data set. And some decisions can be made in a way that's misleading or intuitive. So it seems really easy for me to kind of post hocly criticize a visualization and identify problems or strength. We have to realize, and you probably already realized this from your previous workshop sessions, is that designing a visualization is a very complicated process. And here's how it typically works, right? You have researchers who first collected the data, and you have data scientists that analyze the data and generate insights from the data so they can design a visualization and interactions before it reaches some kind of end user, information consumer, and that information consumer then interprets the visualization. But this process in reality looks more like this because designing a visualization involves a series of decisions, and each design decision can afford a different interpretation. So you can think about this as this mapping between design and interpretation that we are trying to actively explore in the visualization research community here. And the relationship between design and interpretation could be straightforward, or it could be more convoluted, right? Since we have limited time today, I'll give you some examples, and you can imagine how this space is much larger than the number of examples I can provide you is almost infinite. So there's a lot to do in this space. Okay, so example time. We have a visualization here showing it's a intentionally simply designed visualization to show you the durabilities of 2 vehicles, A and B, and their 3 components. You can think of this as like engine or brake or steering wheel. Okay, and if I were to ask you, what is the most intuitive comparison you might make upon looking at this visualization? Feel free to like mumble something in your head about what's stood out to you. If you want to unmute and share, that's fine too. What I'm going to do is I'm going to try to predict what about 80% of you are thinking. And I'm guessing that 80% of you are thinking and noticing that vehicle A's component 2 is much more durable than vehicle B's component 2. And what you mumbled in your head is something along the lines that vehicle A's component 2 is more durable than that of B, but the other 2 are less durable. Okay, now what about this other visualization? What is the most intuitive comparison that you might make upon looking at this one? Again, let's think about it for a few seconds. Feel free to, again, mumble a sentence to yourself in your head. So upon looking at this second visualization, what tends to happen is that you might want to compare the overall durability of A to the overall durability of B and realize that if you sum them up, they're about equally durable. And you probably also realize that these two charts, they're showing the exact same data, but your intuitive reaction is really different. To give you a sense of how we came up with results with predictions like this, we showed hundreds of people charts like this on crowdsourcing platforms like Prolific, and we asked them to write down their top 3 conclusions or comparisons that they make upon looking at this visualization, and we looked at them closely, we categorized them, and we extracted what would be the most probable conclusion that people draw when they're looking at this visualization to eventually obtain results like this. So this is essentially demonstrating that the way you visually arrange your charts will change what people see intuitively from a visualization. And we also try to refer to research from the human perception and cognition side to look for explanations to why this happened. And that allows us to also contribute to theories explaining our brain mechanisms and thus help us explore how we make sense of visualizations. And it turns out that this happens because of the alignments in visualization. So what psychologists did is they wanted to look at spatial arrangements, the effect of spatial arrangements on how easy it is for people to make comparisons. And they found that, so they're asking people to compare these really abstract OVO and OV sets. And what they found is that people can more quickly identify the difference between these two sets when they're vertically aligned like this on the left compared to when they are horizontally aligned like this on the right. So you can see the parallel here. Because it's so effortful to make that alignment comparison on the right, people don't do it, right? Because it's so easy to do it on the left when they're vertically aligned. You want to compare the vertically aligned bars and you want to notice that one is larger than the other. And so what this is saying is that there's these fundamental perceptual mechanisms in our brain that makes certain comparisons more intuitive or less intuitive when we look at visualizations. And so we should design in a way that make sure that what we want people to see matches what their brain intuitively sees. And the fact that even small design decisions like aligning your bars vertically or horizontally can drive different viewer comparisons and viewer takeaways. And that is just one very small example among many, because you can imagine when you're designing a visualization, the number of design decisions you can make is infinite. The space is enormous. And there are many opportunities for us to examine the impact of this design on people's interpretation. And for me, my research program really is trying to formalize this design space so we can build this model that can help us design better visualizations by predicting what the viewer will take away upon looking at a visualization. And so you will have a designer, and this model is supposed to help this designer to adjust the visualization to most clearly communicate some key messages. And here's my kind of proof of concept of how it would work in real life. Let's say you created this chart, and this chart, as the title suggests, is about how people get their news. And this is your first design. And you show it to your model, and the model will make a prediction about how your viewers are going to react. And when you feed this to the model will say something along the lines of, your viewers are probably confused because this visualization is poorly designed. It's too cluttered, too many things are going on. And as a designer, you take that feedback and you're like, okay, let me try again. So you redesign the visualization to look like this. And you show it to your model again. And now your model is going to predict that your viewer will most intuitively see that people most likely get their news from TV and radio, and least likely from their friends. And the model is able to make this prediction because existing work have conducted like empirical studies. And we found that when people look at visualizations, they tend to focus on the top left corner of a visualization, and the prediction tends to fit that empirical result. Although now this second prediction here, people mostly get their news from TV and radio, is an accurate one. It's no longer something about people getting confused. You might not be quite satisfied. Maybe there's something that's more specific about this visualization that you wanted to communicate. So you can redesign this visualization and can feed it to your model again. And in your redesign, you highlighted the internet trend line. And by feeding this into your model would be able to predict that your viewers will most intuitively see that people are increasingly relying on the internet to get their news. And that is the key message that you wanted to communicate. And now the model reassures you that people will see this and everyone's happy, right? So that's kind of what we are building towards. It's kind of our roadmap. But you can also imagine how we can reverse engineer this model to be able to generate a visualization that helps a viewer see a given specific design given takeaway from data. So the example I have for you here is very trivial, but imagine you want to ask the model to build a visualization given this data set that would help people see the message that people are increasingly relying on the internet to get their news. And ideally, your model will say, how's this visualization? Right? And in this case, everyone's happy. We are working actively, my students and I, with researchers from Tableau and Adobe to make this happen. So here I have Tableau's Ask Data interface. And what happens is that the user can type in a question query in natural language, like, please compare the user rating of these two books, and Tableau's Ask Data will generate a visualization that best answer that question. However, this is work in progress, and we run into two challenges that we really need to address as we are trying to perfect this tool. So the first challenge is that what patterns people see in the visualization is difficult. It's hard to predict. And the second challenge is that language can be ambiguous. So interpreting what people are saying or their takeaways is very difficult. So I'll break them down for you with some more examples. So let's focus on the first challenge here. Here I have a visualization. It shows the student government election voting results for two student parties, blue and green, across 4 years. Data is provided for you for 3 years. The y-axis shows percentage support. My question for you is, who do you think will win in year 4? Okay, you'll have, if you want to share.
I would say green.
You say green.
Maybe green.
I'm hearing green and green.
It's
Oh,
a toss-up between green and blue.
it's a toss-up between green and blue. Right. So I want you to feel that that struggle of trying to decide between blue and green, because there's no right answer here. There's no ground truth. We made up this data set with the intention of making people unsure of what might actually happen. And it's possible that you think green wins because you saw that green has been gaining momentum from year 1 to 3, and it's likely going to surpass blue in year 4, or the fact that green is decreasing the gap between itself and blue, and is likely to overturn or surpass it, right? But it is also possible that you realize that blue has won every year, and blue has won most recently. So it is also possible that blue wins, right? So we tried this demonstration with hundreds of people online. We showed them this visualization, and we asked them to rate on this scale. Well, we gave it 0 to 50 as values, but the value doesn't matter. But on the left of the scale would be green likely wins, and in the middle would be a tie, and on the right it will be blue likely wins. And this is what people answered. And what you see here is a bimodal distribution. People are divided on predicting either blue or green wins, and there's like a couple of people who thought it would be a tie. And what they predict really corresponds to what patterns in data that they tended to focus on. So the green color here on the left is people who focus on the increasing trend of green, and the blue color on the right is people who focused on the overarching dominance of the blue. So what's really interesting is that when we took the same data from this bar chart, it's just 6 bars, so it's 6 data points, and we turn it into a table, and we showed it to a different group of crowdsourced participants. Again, there's hundreds of them, and this turned out to be the predictions that they made. And you see that with this table representation, what is happening is that suddenly very few people now predicted green to win. Most of them are blue supporters, because in this table, trends like green gaining momentum is no longer easy to see, and because of that, you're losing the green supporters, and blue's overarching dominance becomes much more salient. So going back to the bigger picture here, what I'm trying to say is that what people see in a visualization, how they react to data is difficult to predict because there are many features and patterns that a person could see within one visualization. And depending on what they choose to focus on or what they can see, we're going to get very different results. And on top of that, the visual features matter, but people could also draw different conclusions from data due to their motivation or their experience or their background knowledge. So, for example, people might think that the green increasing pattern is salient and they're drawn to it because they tend to support underdogs. And they want to believe that the underdogs can win. And if you live in UMass Amherst, you have no choice but to support the underdogs because our football team ranks 130 out of 130 teams in the United States. Besides the point. Either way, it's important for us or for people who are designing visualizations to think about how your interpretation could be influenced by what we call these top-down factors, and that is your motivation, your experience, and your background knowledge. And I have an example here to show you how our motivation, our background knowledge could influence the way we explore data, and to also give you a sense of how work like this is done in a lab setting. Okay, so imagine you collected some data and you choose to plot the data points on a scatter plot so you can see the relationship. And you notice that there is some kind of a weak correlation between X and Y. Sure, and then you suddenly remember, wait, these variables, X and Y, they're actually about the number of environmental regulations and air quality. And you have experience in this area, and maybe you took a course, and you firmly believe that as the number of environmental regulations increases, air quality should be better. So you take a closer look at the scatter plot and you convince yourself that something must have went wrong with these two outlier points. So let's just ignore them and we can just pretend that they're not there, and we can draw a new mental regression line through these data points. And now the correlation looks a lot stronger and it makes much more sense given your existing belief on the relationship between air quality and the number of environmental regulations, right? You can see that this is very questionable practice. So we wanted to see to what extent does this happen in actual visual analysis with data, because you don't want this, right? You don't want people to mentally discount outliers and misestimating correlations in their data set. So to answer this question, we conducted this experiment, and I'll talk about the methodology. So imagine time going from left to right. We first showed chart, a scatter plot that's labeled with X and Y to participants. And at a later time, we showed them the same exact scatter plot, but now they're labeled with real world variables like number of environmental regulations and air quality. And because they're the same scatter plot, we made sure to add this distractor task in the middle to make sure people don't exactly remember what they've seen. And we asked them to make an estimation of the correlation in the scatter plot that they saw. So they could say 0.6 or 0.7 for one of them. And we did this for multiple pairs of visualizations with different real world variable labels. Like we have number of trees in the neighborhood and number of people whose names begin with a T. And we asked them to estimate the correlations for every pairs of scatter plot that they saw. And remember that there is a distractor task. And hopefully that they don't remember that they've seen this exact same scatter plot by the time they got to it. So we tried a variety of real world variable names or variable pairs, and we made sure to cover scenarios where a correlation is not really plausible, like the lawyer and rainfall one, for example. Like it's not really plausible that the number of lawyers living in a county would be correlated to the amount of rainfall in that county. But we also tried correlations that's more belief triggering, like air quality and environmental regulations, or the crime rates and gun ownership in a county or in a vicinity. So with that, we acknowledge that not everyone is going to be an expert on reading correlations. So we made sure to provide some training at the very beginning to teach participants how to read correlations and what it means to have a strong versus a weak correlation. And they have to pass like a quiz of some sorts before they can proceed to the experiment. And in addition to creating these scenarios where correlation is not plausible, versus when it's belief triggering, we also made sure to explicitly ask the participants to report their belief about the relationship towards the very end of the study. So what they actually did is that they just rated on a scale from 1 to 7 at the very end of the study, how much they agree with these verbal statements. Like, I believe that as the number of people whose names begin with a T in a neighborhood increases, the number of trees in the same neighborhood increases. And they can say, I don't agree, or I agree. And you can imagine we do this for all the variable pairs that we do show them, so that we get their baseline belief on how plausible they think these relationship correlations might be. So let's look at some results. So the key comparison we want to make here is we wanted to see how people might behave differently when they look at scatter plots labeled with X and Y, abstract variables, versus when the scatter plots are labeled with the real world variable labels. And just to remind you that these scatter plots are visually identical. So here are some hypothetical scenarios, right? I'm going to plot their estimation on the y-axis, and I'm going to show you the data for these these correlation estimations. So if you see something that looks like this, where the purple is above the orange, it means that real world variable labels would make people overestimate the correlation. But if you see something that looks like this, where the purple and the orange are the same, it means that people are looking at the same scatter plot with X and Y versus with real world variable labels and making the same exact correlation estimate. If people are not biased at all, you would see this, right? If people are not biased by this additional context or their belief, this is what you would see. But you could also see things like real world variable labels would make people underestimate the correlation. So just to remind you that because we asked for people's belief explicitly, we can see how their estimate kind of correlates or changes with how strongly they believe that two variables should be related. So I'm going to plot their reported belief on the x-axis, and we're going to look at how people's correlation estimate change depending on their belief. So weak belief on the left, strong belief on the right. Okay, so for example, if on the left is someone who does not believe neighborhood trees and people's names beginning with T should be related, and on the right, people who strongly believe that they should. But this is aggregated across a variety of scenarios. So there is like a pretty even, uniformly distributed amount of beliefs. And this is what the data looks like. So what we can see here is that people underestimate the correlation for the real world variable pairs. So let's say the correlation is 0.5, but they'll think that it's 0.4 when they don't believe such a correlation should exist. And on the right, you have the opposite. People overestimate the correlation when they strongly believe that the two variables should be correlated. So if the variable correlation is 0.5, they'll think it's 0.6 because they strongly believe that these two variables should be related, right? And we can kind of directly visualize the difference between the real world and the XY here. And what you're seeing here is this positive trend where the stronger you believe something, the more likely you're going to overestimate the correlation when you're looking at the scatter plots, kind of like wishful thinking in a way. And just to cover our grounds, we did ask for their belief at the very end of the experiment. So it is possible that when they reported their belief, they're kind of contaminated by what they've already seen in the scatter plot. You saw a chart that describes some relationship, and you talked about how we asked you how much you believe it. So it's possible that you were primed. And so we did a second version of this where we asked for their belief at the very beginning about these relationships, and just to say that the pattern is the same. There is this belief-driven over and underestimation of correlations, and it doesn't matter when that belief is elicited from people. So the takeaway here is that people, when they look at visualizations, when we look at correlation estimation as a use case, and people's reaction is associated with their belief. The stronger you believe something, the more likely you will overestimate a correlation, the more likely you'll let that belief drive what you think you see, and vice versa. And so going back to what I was talking about, when people look at visualizations, the conclusions they draw will be influenced by their motivation, their experience, and their background knowledge. So imagine you have a correlation that is 0.5. It's like a medium correlation. You have two people looking at it. What's going to happen is that a person who's coming in without a hypothesis, and they're going to see the correlation to be weaker because they don't think the two variables are related. And for someone who comes into this data set with a strong hypothesis, hoping to see a positive correlation, they're actually going to see the correlation to be stronger. And you can imagine how that could be problematic when people are interacting with data, and thus making our life much more difficult as we're trying to predict what people are seeing or thinking when they look at visualizations. Because how they perceive data can be subjected to what we call these perceptual and cognitive biases. And I have some more examples. Since I interface with psychologists, we also just wanted to look at this from a perceptual angle. We do what we call these psychophysics experiments to model how people perceive visualizations. And to spare you the details, some things that we are able to do is that we are able to model how many pixels people tend to underestimate or overestimate a correlation, or sorry, data values when they see it. So when people look at line charts, for example, they underestimate the average line position. And when they look at bar charts, they overestimate the average bar position to about like 5 pixels on a like 1200 screen. Anyway, the details doesn't matter. And what we found is that with visualizations, a lot of the biases that tends to happen with how we navigate the real world, they also apply. So when you look at bar charts that have different aspect ratios, so think about this as like people adjusting the bars to fit different screen sizes. It turns out that when you show people this bar with a wide aspect ratio, people are going to overestimate it. And when you show it with like a tall aspect ratio, people are going to underestimate it. And when you show people squares, they're really good. And it's because we like to see prototypes in the real world, and we want to pretend that everything is more similar to the prototype than they are. So we overestimate this wide aspect ratio, hoping to see it as more of a square than it actually is. And the same case for this tall aspect ratio. And here's another example. But before I give you the example, here's a little background. You might know this already, but there's a famous economist, Daniel Kahneman, who proposed that we have two systems that helps us make decisions. One is called the rational system, and it relies on what we call logical analysis to make decisions slowly. And there's another system, what we call the gut system. It relies on intuitions to make fast decisions. So your knee-jerk reaction. We can see them in action. So here I have a chart showing the number of accidents drivers tend to get involved in. For the drivers that are using this new safety GPS feature and drivers who are not using this new safety GPS feature. What would you conclude here? Again, making you mumble something to yourself. It's tempting to say that, well, drivers who use the new safety GPS system gets in fewer accidents than people who don't. So it looks like the safety GPS system causes people to get into fewer accidents. And that is your gut system at work, right? You're jumping to a conclusion, hoping to find an explanation to the data that you see. And because you've been at school for a while and you probably heard this mantra that correlation is not causation, so your logical reasoning system too kicks in, and you realize that maybe there's a third variable at play after all. People who choose to use the safety system may be safer drivers to begin with. And this took a while. It took a while for your rational system to kick in and to remind you that it's not necessarily a causal relationship that you see. But this is the problem with bar charts in general. When people look at bar charts, which groups data into these bins, it immediately triggers this gut reaction to draw causal conclusions, because we want to explain why are they separated into bins. There must be a causal reason, otherwise you wouldn't separate them into bins, and that's what people think. If you were to show the same data using a line chart, now your knee-jerk reaction would then become people who use the safety GPS system tend to get into fewer accidents. It's not necessarily causal. So with this line chart design, the gut reaction that is triggered is no longer this misguided causal conclusion, but a more correlational one. So the design of the visualization can trigger different gut reactions when people reason with data. And you can compare this case of using line versus bars. And that aggregation of data into bins is really what triggers causal reactions. All right, I think one last example for you. Let's say we're looking at people's income distribution in the real world, and there are 4 groups of people: purple people, blue people, or teal people, blue people, and green people. And this is the reality, right? You make a variety, there's a distribution of income within each group. Like there are some purple people who make a lot of money and some purple people who don't make a lot of money. And same for all the other groups. And then you can show this data using a bar chart, and bar charts tend to show you average value. And on average, purple people make more money than green people. And this is a common representation of income in the real world. You have distributions, but you aggregate them into bar charts. But the problem is that when you show people data like this using a bar chart, what ends up happening in a viewer's perspective is that they're gonna see this data distribution as every single purple person makes more money than every single green person. And that is not an accurate representation of the reality, right? And it can lead to stereotyping. You're going to think, oh, maybe purple people are just better than green people. And that's because you're showing people a visualization that does not help them make the right reasoning to avoid stereotyping. So instead, what you could do is you could take the same data set, but you visualize each data point as a scattered dot instead of showing the aggregate as bar charts. And when you show variability explicitly using this jittered scatter plot technique and communicate variabilities within groups, you're going to help people realize that not every purple person makes more money than every green person. And this is going to be reflected in their mental representation of the data, but also of the people the data is representing. So people are less likely to make these stereotypical assumptions. So designing the right visualization can be very powerful here. Okay, so I'm coming back here, and I just want to say that that's my summary of challenge number 1. What patterns people perceive in the visualization is difficult to predict, and there's all kinds of potential biases associated with this. So it's really important for us to build a foundational model to try to be able to predict how people will react so we can design better visualizations. And the second problem is that if we want to build a model that can predict what people take away from data, we also have to figure out how we can model what people see. And with that, we run into this language challenge. If you recall from the previous results that what we had to do, we have to manually collect data and decipher what people wrote so I can get you these predictions of conclusions, right? So we collected data and made sense of what they wrote, and the aggregate result is what I showed you. But in reality, this process is not as simple as I'm presenting it, because people are not always very clear when they're conveying their intentions. You have this really, so here is a real sentence from a real participant in our experiment. So this is the chart that we showed them. It's very simple. It's 2 reviewers reviewed movies or papers, sorry, and gave them scores. There's 2 papers, paper A and paper B, 2 reviewers and some scores. And this participant wrote, paper A received a higher score from reviewer 1 and reviewer 2. Now, what do you think they are comparing? While you're thinking, I'm gonna move this up. I'm gonna offer you 2 potential conclusions. Okay, so it is possible that they thought paper A received a higher summary score from the combination of reviewer 1 and reviewer 2. In this case, this participant could have added up the 2 white bars and compared it to the 2 gray bars and said the sum of the 2 white bars is greater than the sum of the 2 gray bars. That's one possible interpretation. But it's also possible that the participant meant to say paper A received a higher score from reviewer 1 and A received a higher score from reviewer 2. So in this potential interpretation, the participant compared the white to the gray on the left and the white to the gray on the right, and they noticed that they are both greater than relationships. So there are two greater than relationships. It's like a comparison of a comparison. And which one they did is not apparent to us because this sentence has what we call syntactic ambiguity. It depends on how the participants intended to parse the sentence. They could have meant very different things. So this is what I mean by language can be ambiguous and complex. When you ask people to describe what they're seeing in a visualization, it's not always exactly clear what they saw. And let's just say we did a bunch of study, and if you're ever thinking about going to like natural language processing research, let's say we were able to generate enough insights to predict what people will verbally conclude from a visualization. When we try to implement a tool that like a natural language interface that allows people to input natural language queries, they can still input ambiguous and underspecified language. So we can't control people is what I'm trying to say with this. Imagine we have this simple data set that is about movies. There's information about movie length, box office, user ratings, and movie length. A user could look at this data set and ask questions like, can you compare the popularity of movie A and movie B? It seems simple, but it's impossible for the machine to understand what they actually want because the machine could be thinking, what do you mean by popularity? Do you mean box office? Do you mean user rating? Do you mean a combination of the two? But how do you like to combine it? I don't know, right? The machine panics and you can't actually answer the question. So that's hard. And the user's like, fine, I'll ask you something more straightforward. Since you have the variable movie length, let me ask you to compare the popularity of long movies. Great. Actually not so great because what do you mean by long movies? Do you mean long as in higher than average in the data set? Or do you mean like top 10 percentile? Do you mean anything over an hour because you have no patience? I don't know. So the machine panics, the machine cannot answer these questions. And one solution that we're working with researchers from Tableau and Adobe is to think about how we might resolve the ambiguity by showing people visualizations that best answer their questions without having to answer these more specific fine-grained details about their answers. So what we did, we interviewed a bunch of people. We asked them these confusing questions that real people would ask in the real world. And then we asked these people to draw for us what visualization might help them explore the data set and resolve their ambiguity and get them what they want without having to figure out how long is a long movie. And we came up with these like top 4 visualizations that are candidates to answer these questions for each type of ambiguous command people give. So for example, if someone asks you to compare a highly rated book with a similarly highly rated book with respect to price, the system could show charts like this or this or this or this. And following this, we did a second study where we asked real people, if this is the question that you were asked, which of these 4 visualizations do you think would help you answer this question the best? And then they pick one. And then we asked hundreds of people. And the consensus is that for this specific question, the top left way to visualize it with this bar chart and this highlight is the most preferred. And we have much more detail in this paper. You can check it out, but I'm just hoping to help you see that this is not an easy task, right? And this whole space is going to be very helpful in the long run, but we have these challenges about predicting what people see and trying to understand language that we have to kind of overcome before we can build a model like this that predicts viewer takeaways and generates visualizations. I want to wrap up with one last thing, so 5 more minutes for me, because since we're now thinking, I'm trying to think about the interface between visualizations and perception and policy, and I'm working with people to think more about this space because I realized that because I interface between visualizations and perception, that is really an interface between technology and humans, and when you interface between technology and humans, you have to think about implications of computer science research on our society. So as part of this like revelation, I joined what we call the Human Factors Task Group at the National Institute of Science Standards and Technology. And my job is to identify opportunities for cognitive biases and provide inputs to writing practice standards and guidelines to help scientists and practitioners make better decisions. They said it really well, and I just copied and pasted what they said. So anyway, thanks for dealing with this mouthful. And in my endeavors, I begin to realize that there's one critical topic that drives decision-making with data and that drives how things are done in our society, and that is trust. So trust is an important topic that we are expanding our research program into to look at how visualization and trust interacts with each other and how we can create guidelines to help people make better decisions through enhancing trust. But there's a lot to say about trust. First, trust is a dynamic process, right? In visual data communication, the reader can choose to trust or distrust a visualization. The visualization can have high or low trustworthiness. But the issue is that sometimes the visualization is the only contact the reader has with the underlying data, and there's not so much back and forth between a person and some static image, right? So the question is, how can you elicit the most amount of trust in this single value exchange? And what I'm arguing is that we can design visualizations to drive critical thinking. And once you get people to critically think, you have more, you're creating more opportunities for this internal reflection for people. And we know that there are design choices that we can intentionally do to increase critical thinking. And potentially increase trust. I don't have time to talk about this, but I am happy to share some preliminary work that we've done in this space. And just remember the key takeaway here is that you have to show the right level of data complexity. You can't show things that are too simple or things that are too complex to enhance critical thinking without sacrificing comprehensibility. Okay, that's the takeaway. Not too simple, not too complex. And another thing that you want to think about is when you increase critical thinking and when you're increasing trust, you have to think about what kind of trust you're trying to increase here, right? And I argue we should think about trust in a calibrated fashion. So you want to get people to critically read your data to not over or underweigh the evidence when they're making decisions, right? They shouldn't take it for granted and they shouldn't question everything. And so we kind of establish this relationship between the amount of information you show to people and the amount of trust that people will have. On one hand, it's a curvilinear relationship. On one hand, if you show people no data, you can't expect them to trust it because it's like a black box, right? How can you trust a black box? And on the other hand, if you're overwhelming your audience with a lot of data, it's going to clutter their visual system. It's going to put too much cognitive load on their brains, and the information is not legible, and it's just going to create opportunity for bias. And the joke I have is that you have these like boom of machine learning models in the world, and you can't just say, here's your black box machine learning model and expect people to trust it and to use it because they won't understand it. But on the other hand, you can't tell them everything there is to know about the machine learning model because you're going to overwhelm them and they're not going to trust you because they don't understand what is going on. So aim for this optimal space where you're showing them just the right amount of information without hurting trust. And the last thing is that trust can be very contextualized. Depending on the situation, our threshold for trust can change. So imagine using an app to decide which route you want to take to drive to a park versus using an app to decide which route to take to evacuate from a city when there's a hurricane. You might have different requirements and thresholds for the app to deem itself trustworthy. Okay, so context matters, and I have one context that we're working in nowadays. I'm working with sociologists and political scientists and district attorney's office to study trust and visualization in the criminal legal domain. But quickly, some background. Hope you already know this, but the US criminal legal domain is very complex. Legal professionals like prosecutors and analysts in district attorney's offices, they have to make a lot of decisions every day. And the complexity and the scope of these decisions are not always communicated or made aware to the general public. And here's a flowchart to give you a sense of how complex it can be. Okay, you don't have to read anything closely. I just want you to feel overwhelmed because this is overwhelming. I don't even know what most of these words are anyway. And what I want you to know is that a lot of discrimination can happen in this process, and the opaqueness of this process is making the general public lose trust and faith in the legal system. Okay, and so because of that, there has been growing demands for change, and prosecutors and district attorney's office have this potential to play a major role in this change. And some prosecutors identify themselves as progressive prosecutors, and they're pushing for change through data transparency and dissemination. And from my perspective, for visualization people, this means that they're, well, what they're actually doing is that they're creating these online data dashboards. And the online data dashboards really vary between county to county. So just to give you some example, this is one from Multnomah County in Oregon. This one is from Lake County in Illinois, and this is from Yolo County in California. All on the same page for you. You can see there's no standard for how to design these. And we are curious to see, how does sharing these criminal legal data via dashboards impact public understanding and trust in the legal system? Because the question is, should they be standardized somehow? Will there be any repercussions for not standardizing it? So we showed people these dashboards and we asked them questions like, how much do you approve this DA? How much did you understand the information? How much do you trust the data? And what you see here is that there is a difference. Yolo County is much more trusted and approval rating is much higher when people look at these dashboards for various reasons. This is again work in progress, but the design of the visualization dashboard seems to matter. But I do want to say work in progress. We're in the process of trying to figure out what about these dashboard that makes people trust it more or less. So in visualization and trust has a lot of policy implications that has yet to be explored and really deserves further thinking and exploration. All right, I think that's all time I have. So I'm going to quickly summarize what I talked about. Number one is that visualization design really changed how people understand data and make decisions. And to solve this problem, we need to create descriptive models of how people actually understand visualizations and to map how natural language descriptions of user intents can be mapped to patterns people see in data. And I mentioned this last bit about trust in visual data communication. And there's a lot to do on the progressive prosecution aspect with regards to data transparency. And if you remember nothing from this talk 5 years from now on, at least try to remember this, is that you have a lot of power when you design visualizations. So please design it thoughtfully. That's all I have. Thank you.
And mute it so you can hear the applause.
Thank you for the applause.
That was a really awesome talk.
That was so cool.
Y'all
Wow.
too kind.
It's really interesting because we had actually the Los Angeles district attorney here last week or 2 weeks ago.
2 weeks ago.
2 weeks ago. And he's a progressive prosecutor. And yeah, we've had him here twice actually to talk about like evidence-based policing, and I think this is the stuff that he's really interested in, just like how to, public perception on his record and stuff. So yeah, that's really interesting.
Yeah, is there any, I know you just mentioned it's like a work in progress, but is there kind of any, like, is there any work that's been done on kind of in this field of kind of like trusting data visualization and kind of in terms of the policy space? Because I think it's pretty common experience that people have that not just in this use case, but also in a lot of different, especially like government related things where their dashboards are awful and nobody trusts the data. And yeah, I guess like I guess the question is kind of like, what have people really looked at this, or is this kind of the first like foray into that space?
Yeah, really good question. I mean, I'm surprised to hear the connection with the LA district attorneys. That's really cool that so you can see this is like a growing space, a lot of interest. So to kind of answer your question, Kayla, like people are not really looking at the implication of dashboards specifically, but there are growing momentum to look at trust and visualizations. And I think this work has to start slowly. Dashboards are very complicated, right? And people are maybe still looking at just given one visualization, what do people care about when it comes to trust? Do they care about the source? Do they care about the design? And dashboards kind of augment that because you're throwing multiple visualizations at it, and maybe it's interactive, and maybe there's multiple different contexts. And as I mentioned earlier, like the domain really matters. People might have a high bar for criminal legal data, but a low bar for fitness data, right? So yes, it's a work in progress. We don't know much, but what I can tell you from what we've been studying in our lab recently is that you want to have a good balance between, well, not just my lab, but also the trend or existing work in the data visualization community, is you really need a balance between the amount of text that you provide people and the number of visualization you provide people. It's not great if you have no text, and it's not great when you have too much, right? So, but how much text is a good amount of text is, again, depends on lots of things like personal preference, for example. Experts tend to want more text, whereas novices in the domain, novices would prefer less text. So that's kind of where we're at with regards to new findings that I can share.
Yeah, I have another question, but does anyone on the Zoom or in here have any other questions? Or
Question. Hello. Thank you for your talk today. It was really wonderful. I'm really curious about the tool that you're developing with Adobe and the other and Tableau for natural language input to create visualizations. And the whole like graphic that you that you showed earlier about how you could create a visualization based on what you want to highlight in the data. And I'm curious about whether there have been discussions about like ethical implications of that. Because I could see a case where if that tool becomes widely available, you know, certain actors or individuals might like use data, like might use this tool to highlight trends that aren't necessarily like benevolent, I guess. Yeah.
Yeah, no, you're asking, I really appreciate this question. You're asking a very important question that computer scientists they tend to overlook, this whole ethics component, right? And I've talked to several philosophers about this actually. And you're right, people could be using this technology we developed for evil, but it doesn't mean that we shouldn't try to create something. The analogy that we ended up coming up with these philosophers, who, by the way, just sits in their armchair and think about things in their head all day. They don't actually run new experiments, but they think this solution works. If we can basically increase people's awareness through education or through teaching people about what might be misleading in visual data communication, we could help. It's almost like teaching people who are teaching attorneys about tax fraud, like how people might commit tax fraud, so that when they see it, they recognize it, right? You can teach police officers about how people might commit crimes, so that when they see it, they see signs and they notice it. So you can teach people about how visualization might be used to mislead, so that they can think more critically about it, and they have the tools they need, and they can use these tools to help increase their own ability. And so it's gonna be a long work in progress, but you're right. It could be used for evil, and I posit that this whole critical thinking component might be the solution to that.
Thank you.
yeah, thank you. I have, sorry, one more question as well.
Yeah, of course.
Do you like in your research, do you factor things in like culture or that sort of thing? Like I think I thought about it when you mentioned that people tend to look at things on the top left or focus on things on the top left. And I was like wondering if that's because of where we live and where we start reading things from the top left versus, you know, other cultures that read things from right to left. Sorry. Yeah.
Yeah. No,
and just
yeah.
cultural differences like that, I guess.
Yeah. I really appreciate that too, because I personally only it's a little tricky when you're recruiting participants. And so I have been recruiting mostly, my platform mostly is US and UK participants, but I do have collaborators who are working broadly with the more international community. It's difficult to run these models, and the finding that we're saying that people look at top left, I think they try to get a representative source, but you just have way more data from the US-based population. So the model is very biased towards the US-based population. But what people are doing now is people are actively trying to recruit other people from other cultures. So there's a recent study actually that looked at how people communicate probability and uncertainty with words and with visuals across different cultures. And it turns out, I don't remember the specific finding, but the same word like probably or likely, when you translate it into that same word in a different language, it actually means a different likelihood. This is not true, but sorry, I'm gonna give you an example. It's not true, but it's gonna be like a demonstration of concept. Like if I say the word probably in English, I mean 50% chance. But when I say the same word in Chinese, it might mean 30% chance. And so people are trying to, and not that doesn't apply to just words, it's gonna apply to visualizations. When you show this much variability, people are gonna think, oh crap, in one culture, and I think, oh, this is fine in a different culture. So so we're trying to map this, but it's gonna take a lot of time and effort to slowly build this up, and then not to mention to slowly educate people about this. But you're right, cultural differences is not something that we should overlook. It's just that it takes time, and we're catching up.
Yeah, for sure.
This is really important work.
Yeah.
I mean,
It's so cool. I'm like, I want to switch.
I'm like, I want to
careers.
switch fields now.
You're too kind.
Did you have any more there?
I mean, I feel like I could ask questions forever.
I know,
but-
me too. I'm like, I just want to talk to you all day.
Oh my gosh, you're too lovely. Well, you have my contact information. Please feel free to reach out anytime. Seriously.
Yeah, I appreciate that.
Absolutely.
Yeah, and yeah, I was really excited to see the connection of the like progressive prosecutor work that you're doing, because that's kind of been one of our focuses this year. So
Yeah. That's
I'd
really
love
exciting.
to, yeah, keep me posted on what you learn and what you hear. Sorry to cut you.
yeah, for sure. Will do.
Yeah, and thank you so much for that paragraph of feedback too on our previous info. There's not much data in there specifically, but it's still very useful feedback.
Yeah, if you want to iterate it with me, like feel free to send me updated version. I'm happy to take a look again, or if I can be helpful, just let me know. These 2 weeks are a little busy, but once our semester is over in 2 weeks, I'll have much more time. I'll be much more responsive.
Awesome. Yeah, nice to meet you.
Yeah, nice to meet you both. I'm so happy that we were able to connect, and if I'm back in LA, I'll make sure to see if we can meet in person.
Yeah, that would be
Absolutely.
awesome.
Yeah, we'll be here.
All right, sounds great. Well, I do have to run, but
Yeah.
I'll be available on email. You know where to reach me. Good luck with the rest of your semester over there.
So, you
Thank
too.
you, you too.
Quarter. Did I say semester? I'm ashamed
Yeah.
of myself.
Thanks.
Bye.
All right, bye-bye.